I'm Dr. Helen Rees from Jacobs. I'm also the UK representative for the IAG. So if you have any IAG issues, please come and chat to me at the end of the evening or email me. Welcome to our Eggs and BGA evening lecture tonight. Just before we move on to the more exciting part of the evening with Charlotte, I just have a few housekeeping and notifications just to update people on. There's some up and coming evening meetings just to highlight on the slide. So 12th of March, we've got a GES and Eggs joint evening lecture with the past president of the Geological Society, Ruth Allington, talking. And then 16th of June, QRA and Eggs joint meeting with our overseas visitor, Martin Brook from New Zealand, talking about New Zealand landslides. So there are a couple of things that are coming up on the horizon for our evening lecture series, and more information on those and links for hybrid joining will be out on the Eggs LinkedIn site. So have a look on that. We've also got up and coming the 2025 Engineering Group Annual Conference in Cambridge. Abstracts submission is now open. So again, more information on the website. We can start taking bookings for that event. So LinkedIn again has more information that's just been up and posted about that. Final main event that is going to be held along with the Glossop lecture this year in the middle. Don't know why it's doing that, but I'll keep fighting it. We've got the Fuchs meeting, which is being held here in the Geological Society and led by the Geological Society. The Fuchs meeting for engineering geology. Abstract deadline is open for that at the moment till the 10th of March. There's more information on the GeolSoc website. Again, it's continued celebration of Peter Fuchs's life, and we'd really like to encourage particularly our early careers members of the engineering group and other wider parts of our community to come and join us at that event. So look out on the web page for more information. Talking about our early careers, just to highlight our early careers group. For those of you that are not involved in that and want to, fight with the please, again, we've got the engineering group of the Geological Society Early Careers LinkedIn page. There's more information on there. There's a QR code to get to that. Please get involved and engaged. And just a final bit of information. There is free membership to the IAG, the International Association for Engineering, Geology and the Environment. At the moment, if anybody would like to join that, please come and have a word with me at the end of this evening, or again, contact me through LinkedIn or email. As National Group Representative, I can put you in the route to get the free membership if you meet the criteria of 35 years and younger. That will give you free one-year membership and access to a lot of the resources on the IAG website. So that's all from me. It's my absolute delight to hand over to our speaker tonight, Charlotte Usher from RSK, who's going to be talking about demystifying geophysics, how the CIRIA C812 guide could benefit your ground investigation. I think this is a really important document and really look forward to hearing more about, being very passionate myself about geophysics and making sure people use it more appropriately. So over to you. Thank you, Charlotte.
Thank you. And thanks everyone for turning up today and those online as well. So yes, after this presentation, if I can convince at least one person to maybe think about geophysics within their ground investigation, then that's great. So for those who don't know, I'm Dr. Charlotte Usher. I am a principal geophysicist at RSK, chartered geologist, chartered scientist, and also technical lead. But most importantly, I was the lead author for the CIRIA C812 document. So hopefully it means I know what's going on within it as well, and I can let you guys all know why it's interesting. So what I'm going to talk about this evening, and I'm going to try my best to stay to time, I'm going to just give you a really quick overview of the guide. So hopefully that'll give you a better understanding of how to approach a geophysics survey. But the main part of my talk is really going to focus on the applications section. So I've got a lot of real world examples that we brought together within the document, showing geophysics being used for a range of targets and a range of different environments and at different scales. And I'm going to finish this off, hopefully, if I have time, of where geophysics is going in the future and what kind of challenges we think we're going to face with that. There's a lot of jargon involved with geophysics, so I thought I'd just stick up some useful terms and definitions. There is a whole glossary full of these in the CIRIA document, which explains the various terms that we use quite a lot, make assumptions people know exactly what we're talking about. Turns out this is not true. These are sort of things I learned while writing the document. So it kind of made me realize how much we need to maybe explain things a bit better. So what is CIRIA C812? So the guidance was published in December 2023. Has anybody actually read it at all? Good job, a few people, cool. So the key point here is it's a guidance, it's not a standard. It is designed to support people who are looking to commission a geophysics survey. It's not for practitioners of geophysics. It's aiming to hopefully provide you with a better understanding of where and when geophysics is good or effective to use on site. It shows you what good practice in geophysics is. It also gives you the confidence or empowers you to ask questions and not just accept everything that you're being told. Geophysics isn't perfect. It doesn't work every time. These surveys also do not replace intrusive investigations. They work best when they're used alongside them. And this is a kind of a reoccurring theme, is that geophysics is being used as part of a phased investigation or to target intrusives. And we're trying to be honest within the document about the limitations of these techniques. Another key feature of the document is these call-out boxes. So these are aiming to highlight key elements at different stages of the investigation or warnings, relevant warnings, to help you avoid making mistakes that perhaps other people have done. And this is throughout the document, not just within the case studies. And hopefully this will be able to draw your attention to important information. So we've got 5 main chapters. I'm going to briefly summarize a few of them. So this first one covers an important topic of when to use geophysics. Now, obviously, we would always advise consider it as early as possible in the survey design stage. This topic is a talk in itself, and thankfully, I've already got one pre-recorded. So if you'd like to watch it, there's a nice QR code to a YouTube video, or you can search the RSK Geosciences Down to Earth series. This is another topic I could spend an hour talking on, and thankfully, again, I already have. So there we go. There's another YouTube video for you to watch. So this was on choosing the right technique. When writing this document, we were very aware of how science and equation heavy geophysics is. So one of the important things to us was to get rid of that, basically, to simplify it down. We focused on just the main common techniques that are applied on site, where they are most useful to use, what their limitations are, and lots of other helpful information like where sources of noise are and what different outputs you can get. And there's also a nice helpful table within the chapter 3, which shows you which techniques are best to use within certain applications. It doesn't replace going to talk to a geophysicist, but it's a good prompt to help start a discussion. So that's 2 of the 5 chapters covered. What about the rest? So chapter 2, that's where we help to give you a bit of a better understanding of geophysics surveys in general. And you'll notice there's a reference, another C reference there. That's the other CIRIA, older CIRIA guidance, C562, Geophysics and Engineering Investigations, which was published in 2002. Now, while the science within that has largely remained the same, there's obviously been a few updates in technology and software since then. So this chapter is kind of covering that sort of information that's happened in the last 20 years. So, as I said, I'm going to just emphasize a few important questions that you should consider when you're commissioning a geophysics survey, either to your geophysicist or to yourself, to help get the most out of the survey. So what do we want from a survey? We want something that is cost effective. We want something which will help us avoid surprises on site, but also will give us the information that we want. The more information you can provide your geophysicist, the better the outcome is going to be, and the better designed your survey is going to be. It may be helpful for your geophysicist to visit the site. They will have a better understanding then of any access restrictions or any physical obstructions that may hinder the surveys. They'll also be able to better assess for any sources of noise on site. So this would be anything that causes an uninterpretable measurement that may mask signal. If you're in any doubt over whether or not geophysics is going to work, your geophysicist may suggest a trial survey, which can be used to test methods to see which ones are feasible or not. This is not a reconnaissance survey. That is a first phase survey that's used to rapidly map out the site and can help to identify features to target in later phases. Finally, having experience in the geophysics survey that they're using is vital for all stages of the investigation. And the same is true for obviously processing and interpretation. Any interpretation of the data that's been provided is going to potentially have a subjective bias, as it would in any situation. And inexperience with a technique is obviously going to add ambiguity and uncertainty to any conclusions and potentially make them wrong. So it's good to check, does your geophysicist understand what is usable data and what is noise within their data record? How certain are they about their results? Have they quantified that certainty? Take everything with a pinch of salt, as they say. Now on to the interesting bits, the real life examples. So, as I said, I'm going to look at the applications of geophysics. We've got 4 main areas that I'm going to focus on. Each of those is split into subsections that reflect different targets within that application. A key takeaway I want to emphasize here is just because it's worked in one of the examples I've shown does not mean it will work for the same target on a different site. Always ask the geophysicist for their advice. So the first application area I'm going to look at is geological applications. So this is mostly looking at natural targets, such as geological or hydrogeological boundaries or cavities, for example. I don't have time to unfortunately go through every case study in the document. I'm going to try and discuss as much as I can and highlight hopefully some bits of interest to you. So most geological targets are going to represent a significant change in a geology or the stiffness of a material. And this is something that is very measurable generally by geophysics. So geological materials obviously have variable properties such as porosity or shear strength. And a variation in physical properties is the bread and butter of a geophysics survey. That is what we're measuring. Where there is a contrast, we measure it, but we won't necessarily know what that physical contrast is before we go to site. So sometimes the use of multiple techniques is necessary. Not every technique will work in the same way. It does depend on what's being measured. This example here shows 2 techniques being used on the same landslide. So this is at the Holland Hill Landslide Observatory. The image at the top shows an electrical resistivity survey that had really good correlation with the boreholes that were done on site. The seismic refraction survey, which is shown below, was taken on exactly the same slope in exactly the same position, but it indicates a much thicker low velocity surface layer and had poorer correlation with the boreholes. Now, this doesn't mean that the refraction data is wrong. It just highlights a limitation with the technique. Now, the seismic refraction technique cannot detect decreases in velocity just because of the way the technique works, which may not be an issue if what you're looking for is a depth to bedrock, where there is a sharp increase in the velocity. However, if you want more subtle features, this might not be the technique you want to use. This is my first major example. So this is the Havant Thicket Reservoir. Geophysics was used as part of a larger phased investigation. We were looking to map geological changes and determine if this was a suitable site to use for a reservoir. The site was mapped with electromagnetic mapping, which is what you can see in the above image. that looks to around 7 meters deep-ish. And that maps the superficial deposits across the site, basically. Alongside that, 11 resistivity profile lines were completed to cover as much of the site as possible, which covered around 9,400 meters worth of profile lines, down to about 65 meters below ground level. What they were able to observe from this was from the EM mapping data, you can see a blue area in the south, which is the low conductivity Bognor sand. And across the center of the site, we have successfully highlighted the outcrop of the London clay and head deposits, which was matched up to the geological map. Resistivity data showed the thickness of the deposits along these survey lines. And alongside the intrusives, the geophysics data was proved that the site was low risk enough for the reservoir to be put in that location. Overall, the project is expected to cost around 120 million. And by comparison, the geophysics survey was less than 0.5% of that total overall cost. So you've got to look at it as kind of like a big picture sort of thing sometimes. Hydrogeology assessments are usually looking for obviously bodies of water, such as aquifers or depth of water table, as is being shown in this example here. This is actually an interesting use of the geophysics I wanted to highlight here, is the use of the resistivity data to measure the depth of the water table compared to direct piezometer measurements. Now, while the ERT-derived water table depth is slightly underestimated the water table depth during the filling and draining periods, the actual maximum and minimum values of the water table more or less match the piezometer measurements. You can also vary the way you collect your resistivity data, which is done by using different arrangements of electrodes at the surface, which is done automatically by the equipment. And this can be used to either see better horizontal resolution or better vertical resolution, depending on what array type you use. Unfortunately, in this case, they were unable to visualize the base of the gravel mineral, which is what they were aiming to do, to have a resource, a volume calculation. And while they used other techniques, nothing was able to achieve it to the resolution that the client required other than intrusive investigations. So again, the geophysics and the intrusives needed to work alongside each other, but the use of the geophysics reduced the number of boreholes that needed to be used by up to 50%, which ultimately reduced the project cost. This is another example of being able to use multiple techniques. So here we have an erosional target. Erosional boundaries can sometimes obviously be gradational, or the infill material can be too similar to the surrounding materials. So physical contrasts can be difficult to detect. In this case, we had an original river course that had been altered due to milling activity, and they wanted to put it back to its original location as they were having drying issues where it was drying up. The geophysical survey was commissioned to determine where that original channel was. They trialed a few techniques and settled on GPR, magnetics, and ERT. Oh, sorry, not magnetics, EM. My apologies. Ground penetrating radar surveys were able to highlight these lens-shaped objects, which are highlighted in the black lines in cross-section, which is where the radar energy was scattered more due to the fact that they have a coarser gravel infill material. These were then able to be mapped in plan view, and boreholes were used to accurately calibrate how deep they were based on the GPR drive depths. The ERT was able to also be used to visualize the material thickness. We have this brighter region in the center, which the laser is not going to point to, unfortunately, sorry, in the kind of reddy colors, hopefully you can see. That is what we'd expect from a granular channel infill. And all the evidence from these multiple techniques was then used to increase the confidence of the client in the location of that former buried channel. And following a targeted borehole investigation, which was able to be done at much lower cost due to the fact that it was targeted, they were able to restore the original river channel. Okay, the second section is looking at the use of geophysics for determining the physical properties of materials. So it's measuring things like soil stiffness for load calculations. The standard intrusive tests, such as CPTs or SPTs, they only provide data at the position of that sample, and anything in between that has to be assumed. The UK geology is complicated. Assumptions on homogeneity, probably not appropriate most of the time, but geophysics can be used to join the dots between these points. As I said before, geophysics relies on the measurement of physical properties, such as electrical or electromagnetic techniques being sensitive to conductivity and resistivity variation, which is usually linked to things like fluid content. So a lot of these physical properties, a lot of these measurements can be helpful. In this case, we've got an example of seismic surveys being used to calculate the elastic moduli of the ground. An important initial takeaway from this is just using the seismic velocities, we cannot derive the different units that are present in the ground. However, when we use those seismic velocities, the P and the S wave, to calculate the Poisson's ratio, which is shown in the blue and red plot, we can then show more spatial variation and variation in the ground strength and derive those different materials and the different flow zones of the landslide. Another interesting takeaway from this project is they compared CPT surveys to the calculated Young's modulus, which was calculated from the seismic values. And you can see they are very closely correlated, but the seismic data is obviously a lot coarser just because of the nature of the survey, but the general trend of the plot is the same. Some examples in C812 were presented as data examples, either because they were less commonly used or because they were maybe a bit of a contentious subject. The first example is ripability. So this can be calculated very easily from P-wave velocities, which obviously we get from seismic surveys. So the advantage of this is it's a quick conversion, but it is limited by the fact that it has to be done with a P-wave seismic survey or a seismic survey that calculates P-waves, and the results may be ambiguous depending on what Ripper chart you use compared to what you're digging up with. So there may be some variation in terms of how things actually end up being removed from the ground. Soil corrosion, this is one of those contentious subjects I was talking about. Corrosion in the soil is obviously from degrading metal based on a chemical reaction, and it's hazardous to critical infrastructure like oil and gas pipelines, for example. It is directly related to the resistivity of the ground, so we want methods that are sensitive to this. Point measurements, which is the way they would traditionally do it, they will only sample an individual position, much like intrusives. So it's more efficient to use an electrical resistivity survey along the line of the pipeline to get that lateral continuity between your points. As you can see from this example, there's actually a lot of variation along the route. And so this added detail can then help with calculating any remediation costs. Another method that uses more point-based measurements is earthing studies. So we tend to use vertical electrical soundings for this. There's a lot of existing standards that tells you exactly how to do it. But again, the surveying comes with a lot of assumptions. So we're assuming continuity between the sample points. We're assuming the layers are horizontal within the ground. And we're assuming that, well, and unfortunately, higher ground resistivities are going to limit how deep we can survey. If we want to have the actual resistivities of the ground, we also have to invert the data. So because when you take the measurement, it's just an average from the surface. So when we invert something, we take a model of the ground the way we think it is, either from a borehole or from knowledge that we've got of the actual structure. And then we calculate what the measurements would be from that model. And we keep doing that until we find one that matches our measured results. We can use boreholes for context. That is helpful and obviously wise to do that because then they have the structure of the ground. But what I want to highlight is picking your borehole can be tricky. So if we take this site up the top here, there's a borehole quite close to it that we could use, or we could use one down the bottom end of the site. The blue crosses mark the measured data. The blue crosses are the modelled results. The green lines mark what has been measured. So as you can see, when you use the borehole that is close to the actual location of the survey, it matches really well at depth, but not quite so well at the top in the shallow subsurface. Whereas when you use the one that's further away, ignoring the layer of peat, it matches well at the top, but not at the bottom. So you're not always going to have a perfect match, even if you use one right next to it, but often it is better to try and use one that's close to the location if you can. Many geophysics methods that I've mentioned can be used in boreholes using specialist tools. This ends up logging the ground immediately surrounding the borehole. This was an example presented in C812, which shows wireline logging used to determine physical properties, aiding in a site investigation. So in this case, it was measuring NAPL content. It's a very wide subject area, geophysics in boreholes. There are a lot of guidelines that exist, but some of them are a bit dated. There is currently a CIRIA proposal out on wireline logging. If anybody is interested, that is the contact details of who is running that. But wireline logging provides useful data. It can help separate units that have different physical properties that may look visually the same. It's also the fact that we have this potentially physical difference that's not visible is why we have a difference between visual borehole logs, the standard logs, and geophysical survey depths occasionally. Our next major area is environmental applications. So this covers any materials in the ground that could be hazardous to environment or human health, or the leakage of fluids from boundaries that should otherwise contain them. And in many cases, you either have to look for the actual fluids themselves or the containers that they should be in. My first case study here is a landfill site. So in this case, they were looking to redevelop the land for residential housing. They were looking to excavate, screen, wash, and reuse as much of the waste as possible. So an accurate determination of the volume of the waste was really critical for financial viability. A combined geophysics and intrusive investigation was used. They started off with an electromagnetic mapping survey shown in the top left. And fortunately, the contents of the landfill, which was mostly commercial waste, was really conductive in comparison to the actual surrounding material, thanks to the leachate that was contained within it. That's shown by the warmer colours and outlined by the dashed line. The boundary of that waste was able to be mapped to within a metre accuracy. They then used electrical resistivity to try and quantify the depth. There was mixed results with this. Unfortunately, the resistivity of the waste was a bit too similar to what was underneath it. And so it was difficult to delineate where the boundary was across the entire site. Boreholes were key to providing this continuous depth and then producing a fully robust model of the landfill. However, the final waste estimation that was produced was within 0.3% of the total volume that was actually removed. Over 90% of that waste was then able to be reused in the development area, and this accurate volume calculation obviously then helped to produce a really accurate remediation cost and provided an overall cost saving for the client. It does work sometimes. This is an example again of another waste situation where ERT has been able to successfully determine the depth of the waste, and that matched really nicely to the lateral extent that was measured by the electromagnetic survey. As already discussed, electrical resistivity, really good for measuring the presence of fluid. The benefits of it's not just limited to one sample location, and also, the key thing here, the results are repeatable. Unlike lab samples, you do not have to destroy the sample. You can do it in exactly the same place over many months. And that's an example of what's going on here, which means it can also be used to measure fluid flow over time or changes over seasons. But you must account for changes in the weather and the ground conditions, as that can affect your interpretation. Now, this is a really nice case study. I'm looking at buried tanks and drums. These are obviously both an environmental issue and a buried hazard, though that does depend on what the contents are and what the construction material is. What the tank is made from and how it is buried will affect the geophysical measurement. So some tanks are buried directly into the soil, maybe have a series of pipes connecting them to other features. Some tanks are buried within chambers, and some tanks are buried under reinforcement, which can mask the signal of them. This case study example was in Greece. It was a former military camp. They were made aware there was 3 underground storage tanks on the site, but they didn't know where they are, just the vague area of where they were. So they were surveyed with multiple techniques. Initially, they did a ground penetrating radar survey. This highlighted 2 anomalies, which you can see in the top right, circled in white. And then a third set of anomalies were shown on the left, which were 2 linear features which were thought to be some sort of buried utility. The blue feature that's shown next to them, that was a surface concrete pad, and there was nothing could be seen underneath that, but it was assumed that it was just some sort of utility situation going on. The MAG survey that was done in the same area, that highlighted a number of anomalies that can be shown, that's shown in the bottom left image there. Some of them overlay the GPR anomalies, and 2 were further significant signals. The one to the far west of the site was again ignored because it was assumed that the MAG signal was just due to the reinforced concrete. And the 3 anomalies in the east were targeted with further electrical resistivity surveys. Now, a metal tank buried within the ground, which is what we were expecting these to be, we would expect to see that as a large magnetic signal and then a low resistivity anomaly, which we do see in the top of the ERT features, which is ERT line 1, which is the one that's furthest to the west. Now, the one that's furthest to the east, they actually saw a large high resistivity anomaly, which is completely the opposite of what they were expecting to see. When they dug them up, they actually found that the one that showed the expected anomaly, that was indeed a metal tank buried directly into the ground. The one, however, that showed the high resistivity anomaly was actually a tank buried in a voided brick-lined chamber, which is the fact that we were actually measuring the void there rather than the tank itself. Now, they also dug up around where they found those utilities, and they did indeed find the 3rd tank, which is just to emphasize, just because you can't necessarily see a target of the tank does not mean it is not there. They made assumptions here that it wasn't, and that would have been incorrect in this situation. If there is a hazard to human health, obviously, if there's pathogens like you would expect to get from a foot and mouth burial pit, you don't want to touch the ground. You do not want to dig up any of the ground here. So using non-intrusive surveys is going to be key in this situation. We want to affect the ground as little as possible. So in this case, they were able to survey the ground with multiple techniques. Electromagnetic surveys managed to outline a feature in the ground, which was then confirmed by a resistivity survey to find the area of the suspected burial material. Finally, buried artifacts and hazards. Now, this is arguably the most common application of geophysics. It covers a lot of near-surface obstructions, things that pose a risk to existing infrastructure or proposed new developments, often used on brownfield sites to identify things like foundations or reinforcement or unexploded ordnance. And obviously, historic mine workings are a big deal in the UK as well. Ground penetrating radar is used in a lot of these situations. It's a really great reconnaissance tool. It is versatile. It can produce high resolution data in 3D, so you can view it in cross section or in depth slices, as I've shown you examples of today. There's multiple frequencies we can use, which means we can either see a lot of detail in the very shallow surface or slightly less detail, but a lot further down. There's existing guidelines for things like utility detection, such as the PAS 128 guidelines. That describes the best ways to detect utilities. It's not a legal requirement to use it, but I would strongly advise that you do, especially if you want to be safe when breaking ground on site. This is an example of when it wasn't used. So this site was surveyed with just electromagnetic location. They hand-pitted a trial pit around this location and managed to locate 3 plastic pipes, one of which was a gas pipe, in the area that they hadn't been able to map out. These would likely have been detectable by GPR based on the depth and the surface. And imagine the danger they would have faced if they hadn't hand-pitted that. Another thing GPR can be used to do is map road construction layers or metal reinforcement bars. Now, generally, we would advise that in this situation, cores should be used to validate the depths along the profile, but then the GPR can be used to measure the variation in between those sample points. it should be noted that the majority of GPR will generally be processed with a constant velocity to simplify the processing steps, but that might not be true if you've got variations of moisture content along the profile line, for example. Obviously, using geophysics in archaeology is a well-established technique to help reduce trenching. Largely, they use surface mapping techniques that can survey with a fine detail, but don't break the surface and therefore damage any features. This example is a site near St Albans. We had some really nice mag data from this site, which was able to map walls and ditches of the old settlement. The images at the bottom here show the GPR compared to the magnetic data, which obviously is showing some quite nice similar features. Unfortunately, as you can see in the top image, there was a 12-inch gas main running across the east of the site, which limited the detection of features because it masked the signal in those locations. So this is an example where the buried utility was actually noise in this situation because it can't be removed from the data. Foundations and pile depth is a really big section. There's loads of case studies being presented in this to highlight the different ways that geophysics can be used to map out foundations. We want to be able to accurately map them because it can help with any redevelopment costs on brownfield sites. But if we're unsure of where they are, or we want to confirm their position, then surface mapping reconnaissance surveys are going to be the way to go. They can rapidly map out the positions, and then you can target your intrusives, which is what was done here. So I'm showing an example that's in the bottom right corner. And as you can see, this electromagnetic mapping target was actually a brick-lined tunnel in this instance. You can also use these surveys to map out features like pile foundations on the site. And then if we want actual detail on the pile foundations, such as the depth, we can use a borehole survey next to the pile. We can put a seismic survey within that to work out the depth of the actual structure, and hopefully a mag survey if it is reinforced. Though I should emphasize that often the reinforcement doesn't go down to the base. So if you were to just use a magnetic survey, which is arguably quicker, you may underestimate the depth of the pile. Alternative methods that we could use, not as commonly used, but sometimes you've got to think outside the box. Things like microgravity can be used to measure where the denser materials are at the foundations of structures, or electrical resistivity, obviously, to look at any contaminants that might be in the ground. Similar methods can be used to detect evidence of mine workings. So obviously the voids from mine shafts can present a significant risk to future development or existing structures. It's estimated around 130,000 buildings within the UK are within 20 meters of at least one known shaft, and that only accounts for the ones we know about. Typically, we would use surface mapping techniques such as GPR and MAG to reconnaissance a site, or a rapid cross-section method, for example, to identify any surface features or shallow anomalies that may indicate mining activity. So things like rail tracks or a cap feature. These can then be used to either optimize an intrusive investigation or further geophysical surveys, such as here, where they used microgravity to locate a voided cavity and shaft. And that using this targeting also helps to make these more detailed options more cost effective. Animal burrows, these exist as a void in the ground. They can damage man-made embankments, particularly those created for flood protection. Generally, we want to try and image these without disturbing the animals. We have a lot of issues with the sort of materials these are constructed with, in that the type of material, if it's clay or saline based, that can limit the depth penetration of certain electromagnetic techniques. And some techniques that are sensitive to voids, such as resistivity or microgravity, may not have the resolution to be able to visualize these centimeter size holes. This is actually a good example of resistivity and GPR being used to detect the extent of animal burrows. So in this case, it was in a levee structure near a river. The fact that the levee structure had an increase in elevation away from the river, and the fact the burrows were still flat, meant that the position of the burrows from the surface increased. Unfortunately, that meant it went out of the resolution of the GPR. However, the ERT, the resistivity, was able to map out the actual lateral position of the boreholes, although it did slightly underestimate their depth. Finally, again, it's a wide topic, unexploded ordnance. It has its own CIRIA document as well as various other guides. This is just an example to show you that while it is very nice when you've got a nice greenfield site, you can very easily show a UXO, an unexploded ordnance. When you have a brownfield site with lots of metal clutter on the surface, you may not be able to see it. So just make sure you understand what's going on your site before you commission a survey. It may be pointless. So, final chapter, I'm nearly there. This introduces techniques that are maybe more non-standard to kind of like highlight where we're going with geophysics and advances that we're moving towards, as well as highlighting some challenges that those things still face. So, some of these technologies are already being applied more regularly, particularly to engineering style ground investigations. But some are still in development for commercial use. So the first part of this chapter discussed physical platforms. So these will be the mechanism from which technology can be used. So this main focus of this was drone technologies. So there's a lot of development within this. Some techniques like magnetics have been well established, so well established they have their own specific guidelines, in fact. Others are still in development. The next section of this chapter in C812 discusses specific technologies that can be used. Certain technologies, such as the willow stick, they're not new, but we felt they were worth mentioning. There's mixed feelings about that technique in particular. It needs a proprietary instrument and inversion algorithms. There's no generic kit for that, which makes it a little bit biased. SAR, that includes any measurements from satellites or drones or ground-based systems. So a bit of an overlap with the previous part, but it's well established for measuring things like subsidence, and there's other investigations going on in measuring moisture variation. It does need line of sight access, but it does prevent the need for physical access to areas that may be unsafe, much like drone technology. Distributed acoustic sensing, or DAS, that's very similar to seismic techniques. It measures the physical vibration in the ground, but it uses fiber optic cables, which are a lot cheaper to use, and they can be installed within structures, which is what was the case in this example, where they installed a DAS cable within a dam structure when it was constructed, and they were able to use that DAS to measure defects within the dam structure, which had been placed there deliberately, but the people who were surveying didn't know where they were. But they were able to map out a number of these defects. Advanced gravimeters, so this is microgravity technique. So this includes things like quantum technology, which the instrument you can see, the large blue one, that's a quantum gravimeter. They're significantly larger than their commercial equivalent, and they have very large power demands, but they have the potential to be far, far more sensitive. It also includes MEMS gravimeter, which uses the same technology as the accelerometer within your smartphone. Although they're still in development, they are a lot more cheaper to make than the current technology, and they are almost as sensitive. Cosmic ray muon tomography is another one that's mentioned. This technology, again, has been around for a while, but the detectors have been slowly decreasing in size, making them easier to use. Cosmic rays are naturally occurring fundamental particles, so this is a passive method that doesn't require any energy to be input. They are in the Earth's atmosphere naturally, and they can be used to measure density, so measuring voids in the same way we would with microgravity, which is what they're doing here, measuring for shafts within a rail tunnel. A limitation of this is that because obviously the muons are coming from the sky, the detector has to be placed below the target of interest so that the muons can hit the detector. Finally, data management. Now, the buzzword for this would be big data. As the amount of data we have increases, we have to change the way we store it and process it and interpret it. We can't collect 3D data in the same way we would collect 2D data, and then turning that into 4D data makes it even more complicated still. Some multi-channel GPR systems can produce terabytes of data from just one survey. So this section looks into how machine learning has developed in terms of things like automatic processing, And machine learning is going to be required as data sets continue to get larger. The takeaways from that at the moment are that object detection is really quite difficult to code in certain situations. Features like hyperbolas in GPR, which is how we would detect a utility, for example, they can be at a different depth. They can be variable strengths in how much energy is reflected back. And they can also be variable in their shape, even for the same feature in between lines. And that makes it very difficult for the machines to actually learn what it's going to look like. Thanks for listening. That's the CIRIA document. I'm just very conscious I was running out of time there.
We now have time for a few questions. Also online, if there's anybody with a question, please type that in, and we keep an eye out for anything that's coming from our hybrid listeners. I open the floor now for questions.
Would you consider that geophysics is underused in ground investigations in the UK? And as a geophysics practitioner, how do you think we can encourage more application of geophysics in ground investigations?
CIRIA document, obviously. Yeah, I would say there are certain people who are very good at using it, but then it is also underappreciated in other situations. So the short answer is yes, I do think it's underused. And I think that the only way we can help improve that is by helping people's understanding of how it can benefit their ground investigation, to help encourage them to think about it, even if they don't end up using it. It's the getting them to think about it first is the really important thing.
If you can just introduce yourself, your name and your organisation, that'd be appreciated.
Scott O'Neill, Mott MacDonald. Thank you very much for that. First of all, I thought it was great to hear somebody in the world of geophysics, and I'm going to lose friends here, actually admit that it should be used as part of a suite, and it's not the answer to everything. And by extension of that, many of us here are probably used to sitting in a room where we try and champion geophysics as part of a larger survey and study. And I have certainly been in rooms where clients have said, so you're telling me that we'll spend all this money and then you'll still have to go and drill some boreholes. So what would be your advice of how we could best sell the services of yourself and other geophysics practitioners?
I'd say that the main things we found is there's two things that put people off using geophysics. One of those is the cost, as you bring up, but often that is when people use it reactively later on in a situation. They've already budgeted for the program, they've started, they've come across something unexpected, and then they've got to do a geophysics survey because they're panicking. And that is when it's going to cost the most. So this is why we always try and emphasize people use it early on. And it's also why we're pushing for this sort of situation to talk to people about it, but also the bad experience element. That is the other thing that puts people off. And it's kind of like if you have somebody who's rocked up to your site and they say, oh, I'm going to do a GPR survey, but actually the results they've provided you are useless, you know, to put it bluntly, it's going to put you off. Or they're misleading and they end up costing you more money. It's going to put you off. It's not going to make you want to do it again. So actually having a definition of what a competent geophysicist is, which is what's included in this document, explaining to people what they should be expecting from a geophysics survey so that they know what to look out for and they know when to question certain behaviors, for example. That will mean that more people ensure they're getting proper surveys. And then hopefully that will change the narrative and people will see, oh, actually, they can be useful. Maybe we'll try that again next time. Maybe I'll ask RSK, what should I do on this?
Other companies are available.
Other companies are available.
Thank you.
I notice we've got a question online now from Chris. Thanks, Chris. I'll just read it out for everybody in the room. Airborne EM surveys have been used with success for major infrastructure projects overseas. Why are they not gaining traction in the UK?
I suspect, and they are being used, but it tends to be used in more open areas. So up in the Highlands, for example, I know they use them up there. In the UK, obviously, we've got a lot of existing infrastructure, which is unfortunately going to exist as noise a lot of the time and is going to mask signals from airborne EM data. It tends to be a lot coarser as well, whereas the sort of stuff we're looking for tends to be a lot finer information. That's what generally we find people will use the ground-based surveys for, whereas the airborne surveys tend to be for more coarse, larger changes. So it might be something like groundwater table measurements or even ore bodies or stuff like that. That tends to be what that's used for.
Okay. We've got another one online here now. So how do you quantify uncertainty in the geophysical models, and what methods do you use to incorporate these uncertainties? You just got to go at the bottom of the screen. Gosh, I've now lost it. 2 ticks. These uncertainties into the final interpretation of subsurface features.
Okay.
Oh,
Right.
thank you.
So, quantifying uncertainty will kind of depend on the methods that's being used. In cases where we are doing an inversion, for example, there will often be a root mean squared error that's produced with the inversion as to how well the modeled information fits the measured information, how well they compare. So that's an instant sort of level of the uncertainty that you can provide somebody to see how well this model fits the measured data. There's also things you can quantify, like when you're filtering, how much data you've removed from the data set. And being able to state these things to the client is really important, because obviously I can give you a model where I've removed half the data points. It looks perfect, but it doesn't actually represent what's going on under the ground because I've removed half the data. So having those measures is really important, and that's good practice, is to put that either in the report or on the figures themselves. And that's one of the things we've tried to highlight throughout the CIRIA document, is having those values on there.
One more question online, if that's all right.
Mm-hmm.
So, does the CIRIA guidance provide specific recommendations on integrating geophysical datasets from different techniques to construct a comprehensive subsurface model? And what strategies do you employ to model and validate noise within these datasets?
So I think one of the issues we've had is that there isn't very good integration between geophysics and geological models at present, because people haven't been working closely enough together. And this is something we really need to address within the industry, both from our side and from the geological side. It's something that we're trying to do a bit more. And certainly with some of the more recent projects we've been doing, we've been trying to do that a bit better, talking more to the geologists while we're interpreting our data, considering the actual geological model as we're going along. And similarly, I'm hoping that by integrating a bit better, that will then help us to produce better and more robust models as like a team effectively.
Fabulous. I'll open it back out into Burlington House.
Yeah, hi, my name is Chris Barker from Arup. Brilliant presentation, Charlotte. I loved all the case studies, really insightful. So my question's kind of building a bit on what you were just talking about, is wanting to understand what's the kind of the current state of play and what's the future in the data management, where with ground investigations, we now create digital 3D models. Yep. and we integrate those with our designs and can look at them three-dimensionally. How can geophysics reporting sort of come into that space when traditionally it's a PDF report in 2D? Yes. And you're trying to kind of see how that fits?
100%. Yeah. So certainly what we're trying to push for now is, again, it's part of this integration process. We have software that can produce things that are geolocated. We're starting to use GIS more because, again, that's what our geosciences guys use on site. And the idea is that eventually what we're aiming to move towards is being able to stop producing these PDFs, which, as you say, you're kind of trying to work out where on earth you are, and produce cross sections that have already been geolocated. They're already at the right orientation within the ground, and that people can then look at them in situ on site effectively. That would be the way I would want to move, certainly. And that's what we're trying to do now, is to try and encourage that sort of behavior, because obviously it's ultimately going to be easier for all the engineers to then use, and then they're going to be encouraged to use geophysics a bit more. And it's also going to integrate it better if you're, say, building a leapfrog model. You know, you can upload that data straight into it and then use that to influence where boundaries are, for example.
Yeah, it'd be great if you download onto a tablet and you could walk around site and kind of look in the tablet and say, oh,
That's the
there
dream.
it is there.
That's the dream.
Or the virtual goggles, of course. Anna, do you want to go?
So hi there, Anna Morley from Arab as well. So just to build on that point, this is obviously onshore. So is there a CIRIA guide for offshore? And also, I think we could learn a lot, couldn't we, from like what is already done in the offshore industry, where they do integrate that so much better, work as a sort of geo team. So really, that's just a kind of comment, I guess. And my other comment is, what did they do about those animal burrows? I'm really worried they played like really loud rock music or something, and then all the rabbits ran away, or I hope it was that, and they didn't pump grout in it or something.
No, I don't think they only did that on the BBC. Okay, so in terms of offshore, I believe that was touched on in CIRIA C562. So the original geophysics and engineering investigations. It was chosen not to, again, go back into that for the newer documentation, to focus it a bit down. I mean, it ended up being a massive document as it was. And as you say, it's a world in it's a document in itself. I don't think there's been a specifically geophysics and offshore investigations produced by CIRIA since that first one, but potentially it could be an area they could move into. At the moment, it's just the borehole one that they're moving into currently, but obviously in the future, who knows? If there's interest in it, then definitely. And I do not know what they did with the burrows other than map them, as far as I'm aware.
To clarify, the animal burrows were empty before grouting, I've just seen online. So thank you for that clarification, Jimmy Boy from BGS.
There we go. Yeah, the BGS will know it was a
Yeah.
PhD. So there we go.
So we've also just following up with Jimmy's got a question for Jimmy Boy BGS. Hi, great talk. Glad to see some of our work crop up in your examples.
Yep.
Following on from Sal's second question, does the CIRIA guidance discuss data delivery options between geophysicists and their clients? Delivery options between geophysicists and their clients, I think it should be.
It doesn't specifically discuss the actual delivery of the data. It does discuss the formats that various techniques can be presented in. So whether or not something is a 1D graph versus a 2D cross section or a 3D block, basically, is it discusses like what options you've got for that particular technique. Obviously, when it comes to big amounts of data, we're having to look into different ways when the client wants the raw data, for example, which they do sometimes, how to get that terabytes worth of information across. It used to be we would buy loads of external hard drives, save it all on there, and then post it to them. Thankfully, we're beyond that now, and we're moving more into cloud-based technologies, basically.
Another question in the room?
Oh.
Yeah, thank you. Michael Blakely from AECOM. Thank you for a very well presented talk tonight. To build on the theme from a few questions here and online, I think, take for example, I'm talking about the specification of geophysical surveys. I think, say, for intrusive ground investigation, we've got the ICE book that we all refer to. I suspect it's not as simple as that for geophysics, because there's a broad range of different techniques available.
Yeah.
But I've come across it both in the PDF style report, where perhaps what was asked for wasn't that clear, and therefore the response back wasn't as usable as a client would like, and in language that wasn't that digestible for a layman, but also then extending on into other uses, 3D uses, real world georeferenced. I don't know how far the guide goes, and I'll go away and read it, but do you have any advice around actual specifying of geophysical surveys to help get what the client really wants, and in language that both the geophysicist and a geologist that perhaps isn't specialist in geophysics might understand?
Yeah, so this is a little bit what the guidance was trying to help with, because we are very aware of the lack of standards in this country. And it is something that is kind of like, I want to say loosely in progress, but there is a standard in development, but it's not for anything specific, because the problem is, as with most geophysics, it's site specific. It is so dependent on what you're measuring, where you're measuring, that trying to write a standard that is generic enough to cover like a specific technique is really difficult. And that's been the main hurdle of trying to get one started largely. So up until this point, people are mostly been relying on things like the ASTM standards, which are the American ones, which they're okay, but I think not applicable for every situation, because again, you've got this site specific requirement. So I think what I would advise people to do is, yes, by all means, look at the ASTM standards, look at there are like generic standards for geophysics, and there's lots of papers out there and stuff like that. Start from that, but it may be worth then, when you're asking your geophysical consultant what their opinion is, they could then advise on what actually might be a better approach, because while the standards will define something, it might not necessarily be the most optimized approach for that particular site. Which is, yeah, I'd always advise asking advice. I mean, obviously the standards are okay to start from, but again, yeah, and the language issue, I'm guessing that's also referring to the jargon that we come out with. Again, the guidance is trying to help explain some of those terms, which is why like things like inversion, I've tried to be a bit clearer about what I'm talking about, because yeah, it really opened my eyes writing this document as to what terms we use day to day that actually aren't understood by everyone else. You know, it's talking to our own geologists. They're like, yeah, I don't understand what noise is.
I suspect engineering geologists are just as bad at that.
But yeah.
Thank you.
Hopefully that answered the question.
Time for one or two last questions in the room or online. Last call. If not, Charlotte, I think you're off the hook. Oh, no, we've got a last one. David McPherson, thanks very much. What is the current state of play with machine learning for some of these large data sets? Great question, thanks.
Yes, I mean, there are more things that are coming into play for certain technologies. I'd certainly say there's been a lot of work done on things like auto picking within GPR for certain features like rebar, for example. And but a lot of it is still on the academic level. They're trying to train. The example that I showed at the end of the presentation was GPR data, but it was looking in time slice, so from the surface, to try and get it to look for patterns in the strength of the reflection. So that's another way they've been looking at it, rather than the actual shaping cross section, which is the other way that people have done it. But there's just so many ways you can analyze data. It's complicated. So it's definitely still a work in progress, but it is definitely the way we're going to have to go with when we're getting more and more data. I don't know if the BGS have done more with, like, because they do a lot of time-lapse measurements with their prime system, which obviously gets a lot of data repeatedly. So I know that that's going to their auto processing is something that they've had to look into for that. I don't know if that's gone the machine learning way yet, though.
Super. So final call. Any more questions? Just watch baitedly for the online. Well, I think we're just about there. So Charlotte, that was an absolutely fabulous insight. I think what you've highlighted tonight are some of the real useful chapters and tools that we can use to help us in making sure we use geophysics more appropriately, making sure we befriend of geophysicists from putting out specifications. I know that's something I see regularly in my day job not being done, and it's where quite often geophysics gets wrongly used and therefore, dare I say, abused. Unfortunately. So we've now got this great guidance to help us. We've seen insights in it tonight. There's some tools and links that you've shared as well for people to go away and postulate and take on in slow time. So in the usual way, could we thank Charlotte for all her great work and sharing tonight of that knowledge. So thank you.
That's a link to the guidance, by the way, if anyone needs it.
Thank you all also for participation of our colleagues online, and we've got some lovely thanks and votes of thanks there from people as well. So thank you everybody and good night.